The Magnetars Song, a journey through the universe's strongest magnetic fields. In the vast cathedral of space, where silence reigns, eternal and light travels through emptiness for millions of years, there exist objects so magnetically powerful that they defy comprehension. Stellar remnants that possess magnetic fields trillions of times stronger than anything found on Earth. These are the Magnetars, the universe's most extreme magnetic entities, born from the catastrophic collapse of massive stars into dense spheres no larger than cities, yet containing more mass than our Sun. The story of Magnetars is a meditation on extremes, on how the universe creates conditions so intense that they reshape the very nature of matter and energy. These cosmic lighthouses pulse with magnetic forces so powerful they can strip electrons from atoms at distances of 1,000 kilometers, twist space-time itself, and generate the most luminous bursts of energy witnessed anywhere in the cosmos. Yet for all their violence, Magnetars embody a profound cosmic rhythm, their magnetic fields slowly decaying over thousands of years in patterns that speak to the deeper harmonies governing stellar death and rebirth. To contemplate a Magnetar is to journey to the edge of physical possibility, where magnetic fields become so intense that quantum effects dominate classical physics, where the vacuum of space itself becomes polarized and birefringent, splitting light into components that dance through twisted magnetic field lines. These objects represent the universe's ultimate expression of electromagnetic force, concentrated into spheres small enough to fit within a terrestrial city, yet powerful enough to influence matter across interstellar distances. As consciousness settles into reflection upon these magnetic titans, there emerges a profound sense of the universe's capacity for creating beauty through extremity. The Magnetar sonjects press through radio waves, X-rays, and gamma radiation carries across space the harmonics of magnetic field lines under tremendous stress, creating cosmic music that tells the story of stellar collapse, neutron degeneracy, and the patient unwinding of magnetic energy across cosmic time. In the gentle contemplation of these most extreme objects, the mind finds a rhythm that mirrors the slow decay of their magnificent magnetic fields, a cosmic lullaby that speaks to the deeper patterns underlying all stellar evolution and the eventual return of all energy to the quiet equilibrium of space. The birth of magnetic titans. Deep within the nuclear furnace of a massive star, hydrogen atoms fuse into helium, helium into carbon, carbon into heavier elements in a cosmic alchemy that has continued for billions of years. The star, perhaps 20 times more massive than our Sun, burns through its nuclear fuel with prodigious intensity, its core temperature reaching hundreds of millions of degrees, as gravity compresses matter to densities that approach the limits of atomic structure. For millions of years, this stellar giant maintains a delicate balance between the outward pressure of nuclear fusion and the inward pull of its own gravity. Yet this balance cannot last forever. As the star exhausts successive layers of nuclear fuel, creating elements as heavy as iron in its core, the fusion fires begin to dim. Iron nuclei cannot fuse to release energy instead. They require energy to combine into heavier elements. The stellar core, now composed primarily of iron, begins to cool and contract under its own gravitational weight. The star's fate is sealed in this moment. for nothing can now halt the inexorable collapse that will transform it from a brilliant stellar beacon into something far more extreme. The collapse occurs with breathtaking speed. In less than a second, the iron core, initially the size of Earth, compresses to a sphere merely 20 kilometers across. The density increases by a factor of 100 trillion, forcing protons and electrons to merge into neutrons in a process that floods space with neutrinos. The stellar material becomes so dense that a teaspoon would weigh as much as Mount Everest, while the gravitational field becomes so intense that escape velocity approaches a significant fraction of the speed of light. During this catastrophic compression, the magnetic field threading through the stellar core undergoes an extraordinary transformation. The field lines, initially spread throughout the star's interior, are compressed along with the matter that contains them. As the core shrinks by a factor of 50,000 in radius, the magnetic field strength increases by the square of this compression ratio, a multiplicative effect that can amplify modest stellar magnetic fields into the most powerful magnetic entities in the known universe. The conservation of magnetic flux ensures that the total magnetic field threading through the collapsing core remains constant, but as the core's surface area decreases dramatically, the field strength at the surface increases proportionally. A stellar magnetic field that initially measured a few thousand gauss, comparable to a strong laboratory magnet, emerges from the collapse as a field measuring 10 to the 15th gauss, a strength so intense that it approaches the quantum limit where magnetic effects begin to dominate over all other forces. The newborn Magnetar inherits not only this amplified magnetic field, but also the rapid rotation of its progenitor star's core. The conservation of angular momentum during collapse causes the rotation rate to increase dramatically, much as a figure skater spins faster when pulling in their arms. The combination of extreme magnetic field strength and rapid rotation creates a cosmic dynamo of unprecedented power, where the rotation of the magnetized neutron star generates electric fields strong enough to accelerate particles to relativistic velocities. The structure of the Magnetar's magnetic field is far from uniform, exhibiting complex topologies that reflect the turbulent conditions during the star's collapse. Twisted field lines create regions of intense magnetic stress, while magnetic reconnection events release enormous amounts of energy in sudden, violent bursts. The field configuration evolves over time as magnetic stresses relax and field lines reorganize, creating the dynamic electromagnetic environment that characterizes these extraordinary objects. The surface of the newly formed Magnetar represents one of the most extreme environments in the universe, where magnetic field strengths exceed the critical quantum field by factors of hundreds or thousands. At these intensities, the vacuum itself becomes polarized, exhibiting properties similar to a crystal that splits light into different polarization states. The magnetic field is so strong that it affects the very atoms in the Magnetar's atmosphere, stretching hydrogen atoms into thin cylinders aligned with the field lines, and creating absorption features in the star's spectrum that have no terrestrial analog. The magnetic field extends far beyond the Magnetar's surface, creating a magnetosphere that can stretch across distances measured in light seconds. Within this vast magnetic domain, charged particles follow helical paths along field lines, creating complex current systems that generate radio waves, X-rays, and gamma rays. The magnetosphere serves as a vast electromagnetic machine, converting the rotational energy of the neutron star into electromagnetic radiation that propagates across interstellar space. The birth of a magnetar is thus not merely the death of a massive star, but the creation of a cosmic electromagnetic engine whose influence extends far beyond its physical boundaries. The magnetic field that emerges from stellar collapse represents the universe's ultimate expression of electromagnetic force. Concentrated into a sphere small enough to fit within a major city, yet powerful enough to influence the structure of matter and energy across vast regions of space. The cooling process that follows the magnetar's birth occurs over timescales measured in thousands of years, during which the intense magnetic field gradually decays, while the neutron star's temperature drops from billions of degrees to merely millions. This cooling creates thermal gradients that drive convection in the magnetar's crust, potentially generating additional magnetic fields through dynamo action, while the overall field strength slowly diminishes through ohmic dissipation and magnetic reconnection events. Now, close the eyes and envision this cosmic transformation, feeling the tremendous compression that transforms a stellar giant into a magnetic colossus. Sensing the invisible field lines that stretch across space, carrying the signature of stellar death and electromagnetic rebirth. The architecture of invisible force. The magnetic field of a magnetar exists as an invisible architecture that pervades space around the neutron star, creating a complex, three-dimensional structure that channels the flow of energy and matter according to electromagnetic principles that operate on cosmic scales. This field represents far more than a simple dipole configuration like Earth's magnetic field. Instead, it exhibits a rich topology of twisted flux tubes, current sheets, and reconnection zones that create one of the most dynamically active electromagnetic environments in the universe. The field strength at the magnetar's surface reaches values that approach 10 to the 15th gauss, a magnetic intensity so extreme that it fundamentally alters the properties of matter and spacetime in its vicinity. To appreciate this magnitude, consider that the strongest magnetic fields achievable in terrestrial laboratories measure around 45 Tesla, or 450,000 Gauss. The magnetar's surface field exceeds this by a factor of more than 2 billion, creating conditions where quantum electrodynamic effects dominate classical electromagnetic phenomena. The field lines that emerge from the magnetar's surface follow complex trajectories determined by the underlying magnetic flux distribution within the star's interior. Unlike the relatively simple dipolar field of an ordinary neutron star, the magnetar's field exhibits multipolar components that create intricate patterns of magnetic connectivity between different regions of the stellar surface. These higher-order multipole moments arise from the turbulent conditions during the star's collapse and the subsequent evolution of the magnetic field through various instabilities and reconnection processes. The magnetic field penetrates deep into the magnetar's interior, threading through the crystalline lattice of nuclei that forms the star's solid crust. The field strength within the crust can exceed the surface value by factors of 10 or more, creating conditions where magnetic pressure becomes comparable to the enormous gravitational pressure that supports the star against collapse. The interaction between magnetic stress and gravitational compression creates complex mechanical forces that can fracture the crust in sudden, violent events known as starquakes. The topology of the magnetar's field includes regions where field lines become twisted into helical configurations, storing enormous amounts of magnetic energy in the form of electric currents that flow along the field lines. These current-carrying flux tubes can become unstable, leading to magnetic reconnection events that suddenly release the stored energy in the form of high-energy radiation and particle acceleration. The energy released in a single reconnection event can exceed the total energy output of our Sun over several years. The magnetosphere surrounding the magnetar extends to distances of several stellar radii, creating a vast cavity filled with relativistic plasma that follows the magnetic field lines in complex orbital patterns. The boundary of this magnetosphere, known as the Alfvén radius, marks the distance at which the magnetic pressure balances the ram pressure of the stellar wind. Beyond this boundary, the magnetic field becomes too weak to contain the outflowing plasma, allowing charged particles to escape into the interstellar medium. Within the magnetosphere, the magnetic field lines rotate with the neutron star, creating a cosmic electromagnetic generator that converts rotational energy into electromagnetic radiation. The co-rotation of field lines with the star creates electric fields that can accelerate charged particles to energies measured in tera-electron volts, creating one of the most efficient particle acceleration mechanisms known in astrophysics. These accelerated particles emit synchrotron radiation as they spiral around the magnetic field lines, contributing to the magnetar's luminous output across the electromagnetic spectrum. The magnetic field also exhibits temporal variations that reflect the dynamic evolution of the field configuration over time. The gradual decay of the field through ohmic dissipation occurs over timescales of thousands of years, causing the overall field strength to decrease while the field topology becomes increasingly complex. Magnetic reconnection events can cause sudden changes in the field configuration, releasing energy in bursts that can be detected as increased X-ray and gamma-ray emission. The quantum properties of the magnetic field become important in the strongest field regions, where the magnetic energy density approaches the critical value at which virtual particle pairs can be created from the vacuum. This quantum vacuum polarization creates birefringence effects that split photons into different polarization states depending on their direction of propagation relative to the magnetic field. The vacuum becomes optically active, exhibiting properties similar to a crystal that rotates the polarization plane of transmitted light. The magnetic field also affects the propagation of gravitational waves through the magnetar's vicinity, creating small but measurable effects on the phase and polarization of gravitational radiation. These magnetogravitational interactions provide potential observational signatures that could be detected by future gravitational wave observatories, offering new ways to probe the extreme physics of these magnetic environments. The interaction between the magnetar's magnetic field and the interstellar medium creates bow-shocks and other structures that can extend across distances measured in parsecs. The magnetic field pressure can exceed the thermal pressure of the surrounding gas, creating cavities and channels that guide the flow of interstellar matter, while leaving observable signatures in the form of synchrotron emission and Faraday rotation of background radio sources. The three-dimensional structure of the magnetar's field creates natural waveguides that can channel electromagnetic radiation along specific trajectories, creating directional beaming effects that influence the observed properties of the magnetar's emission. These waveguide modes can trap certain frequencies of electromagnetic radiation while allowing others to propagate freely, creating complex spectral features that encode information about the field topology and plasma properties within the magnetosphere. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments, a quiet echo beneath the stars. The quantum dance of magnetized matter. In the realm of the magnetar, where magnetic fields reach strengths that challenge the fundamental structure of matter itself. The familiar laws of atomic physics give way to quantum phenomena that exist nowhere else in the observable universe. Here, in the intense magnetic environment surrounding these stellar remnants, atoms stretch and distort into exotic shapes, while the vacuum of space itself exhibits properties more akin to crystalline matter than empty nothingness. The hydrogen atoms that comprise much of the Magnetar's tenuous atmosphere experience magnetic forces so intense that they become elongated into needle-like structures aligned with the field lines. The electron orbits, normally spherical clouds of probability, compress into thin cylindrical shells that extend along the magnetic field direction. The binding energy between electrons and nuclei increases dramatically, creating absorption lines in the magnetar spectrum that are shifted to much higher energies than their terrestrial counterparts. The magnetic field strength approaches the critical quantum value, where the cyclotron energy of electrons, energy associated with their circular motion in the magnetic field, becomes comparable to their rest mass energy. At this quantum critical field, approximately 4 times 10 to the 13th Gauss, the magnetic interaction becomes relativistic, and the discrete Landau levels that characterize electron motion in strong magnetic fields become widely separated in energy. The magnetar's field often exceeds this critical value by factors of hundreds, creating a truly quantum magnetic environment. The polarization of the quantum vacuum represents one of the most remarkable effects occurring in magnetar magnetospheres. The intense magnetic field creates virtual electron-positron pairs from the vacuum fluctuations, and these virtual particles acquire a preferred orientation aligned with the magnetic field. This vacuum polarization gives empty space the optical properties of a birefringent crystal, splitting photons into 2 modes that propagate at slightly different velocities depending on their polarization relative to the magnetic field. The propagation of light through the magnetar's magnetosphere becomes a complex quantum process where photons can split into multiple components, change polarization states, or even convert into axion-like particles under certain conditions. The vacuum birefringence creates observable effects in the polarization of radiation from magnetars, providing direct evidence for quantum electrodynamic effects in cosmic environments that cannot be reproduced in terrestrial laboratories. The surface of the magnetar itself represents an exotic state of matter, where magnetic pressure becomes comparable to the enormous gravitational pressure that prevents the star from collapsing into a black hole. The crystalline lattice of atomic nuclei that forms the star's crust becomes distorted by magnetic stress, creating preferential orientations and potentially exotic crystal structures that exist only in these extreme magnetic environments. The magnetic field energy density can exceed the rest mass energy density of ordinary matter, fundamentally altering the equation of state that determines the star's structure. The motion of charged particles in the magnetar's field creates a complex plasma environment where collective effects dominate individual particle behavior. The cyclotron frequency, the rate at which charged particles spiral around magnetic field lines, reaches values comparable to the plasma frequency, creating conditions where wave-particle interactions become strongly nonlinear. These interactions can lead to the formation of coherent plasma structures such as solitons and shock waves that propagate through the magnetosphere, carrying energy and momentum. The magnetic field also affects the nuclear physics within the magnetar's interior, where the enormous magnetic pressure can influence the properties of nuclear matter at densities several times that of atomic nuclei. The magnetic stress may create anisotropic pressure gradients that affect the stability of the neutron star's structure, while potentially modifying the nuclear equation of state in ways that are not yet fully understood by theoretical physics. The quantum nature of the magnetic field itself becomes apparent in the strongest field regions, where magnetic flux quantization effects may play a role in determining the field's structure and evolution. The magnetic field lines can be thought of as quantum mechanical objects that exist in discrete flux states, with magnetic reconnection events representing transitions between different quantum configurations of the field topology. The interaction between photons and the intense magnetic field creates opportunities for exotic processes such as photon splitting, where a single high-energy gamma ray converts into two or more lower-energy photons when propagating through regions of extreme magnetic field strength. This process, which is forbidden in empty space, becomes allowed in the presence of strong magnetic fields and represents a direct manifestation of quantum electrodynamic effects in cosmic environments. The magnetic field also influences the neutrino interactions within the magnetar's interior, potentially affecting the cooling rate and thermal evolution of the neutron star. The magnetic moment of neutrinos, though extremely small, can couple to the intense magnetic field and modify the neutrino opacity and emission rates. These effects may explain some of the observed variations in magnetar surface temperatures and cooling timescales. The quantum vacuum effects extend beyond simple birefringence to include more exotic phenomena such as vacuum dichroism, where the absorption coefficient for electromagnetic radiation depends on the photon's polarization relative to the magnetic field. This effect can create observable signatures in the spectra of magnetars and provide additional tests of quantum electrodynamics in strong field environments. The magnetic field creates natural laboratory conditions for exploring physics beyond the standard model, including potential interactions with hypothetical particles such as axions or other weakly interacting particles. The conversion between photons and axions in strong magnetic fields could create observable signatures in magnetar observations, providing unique opportunities to search for new physics using astronomical observations. The Symphony of Electromagnetic Storms. The magnetar's existence unfolds as a continuous symphony of electromagnetic phenomena, where the interplay between magnetic field, rotation, and plasma creates a cosmic orchestra that generates radiation across the entire electromagnetic spectrum. This celestial music emerges from the complex dynamics of a magnetized neutron star, whose magnetic field undergoes constant evolution through reconnection events, field line twisting, and the gradual decay that characterizes all magnetar systems over cosmic time. The persistent X-ray emission that characterizes magnetars arises from the thermal radiation of the neutron star's surface, heated to temperatures of millions of degrees by the dissipation of magnetic energy within the stellar crust. The surface temperature remains elevated far above what would be expected from gravitational cooling alone, sustained by the continuous injection of energy from magnetic field decay and reconnection events. This thermal emission creates a steady baseline of X-ray radiation that serves as the magnetar's constant song. Superimposed upon this thermal background are the dramatic outbursts that make magnetars among the most violently variable objects in the universe. These bursts ranging from relatively modest events lasting milliseconds to giant flares that can briefly outshine entire galaxies, result from sudden rearrangements of the magnetic field configuration. When magnetic stress within the star's crust exceeds the mechanical strength of the crystalline lattice, the crust fractures in a starquake that can suddenly reconfigure vast regions of the magnetic field. The largest of these magnetic reorganization events, known as giant flares, represent some of the most energetic electromagnetic phenomena observed in the galaxy. In the space of a few seconds, a magnetar can release more energy than our sun produces over several months, creating gamma-ray bursts so intense they can affect Earth's ionosphere from distances of tens of thousands of light-years. The initial spike of gamma radiation lasts only milliseconds, but contains energies equivalent to the total electromagnetic output of our sun over 1,000 years. Following the initial gamma-ray burst, giant flares exhibit a characteristic tail of pulsed emission that can persist for several minutes. This pulsed tail results from the continuing emission of trapped radiation within the magnetar's magnetosphere, where the magnetic field creates a complex resonant cavity that rings like a cosmic bell struck by the initial explosion. The frequency and decay characteristics of these oscillations encode information about the magnetar's internal structure and magnetic field configuration. The radio emission from magnetars exhibits properties that distinguish them from ordinary pulsars, reflecting the unique electromagnetic environment created by their extreme magnetic fields. The radio pulses often show high levels of circular and linear polarization, indicating that the emission originates in regions where magnetic field effects dominate over plasma effects. The polarization characteristics can change dramatically over short timescales, suggesting rapid evolution of the magnetic field structure in the emission region. The rotation of the magnetar creates a lighthouse effect, where beams of electromagnetic radiation sweep across space as the star spins, creating the periodic pulses that allow these objects to be detected and studied. However, unlike ordinary pulsars, whose pulse periods remain remarkably stable, magnetars exhibit timing irregularities that reflect the complex interaction between magnetic forces and stellar rotation. The magnetic stress can create torques that suddenly change the star's rotation rate, leading to abrupt spin-up or spin-down events. The magnetosphere surrounding the magnetar serves as a vast electromagnetic resonator, where various wave modes can propagate and interact. Alpha waves, magnetisonic waves, and electromagnetic modes create a complex spectrum of oscillations that can couple to each other through nonlinear interactions. These magnetospheric oscillations can modulate the observed emission and create quasi-periodic oscillations in the X-ray light curves of magnetars. The interaction between the magnetar's electromagnetic radiation and the interstellar medium creates observable effects that extend far beyond the immediate vicinity of the neutron star. The intense radiation pressure can create cavities in the surrounding gas, while the magnetic field can channel the flow of charged particles across interstellar distances. These effects create nebular structures around some magnetars that can be observed in radio and optical wavelengths. The polarization properties of magnetar emission provide unique insights into the magnetic field structure and plasma conditions within the magnetosphere. The high degree of polarization observed in many magnetars indicates that the emission originates in regions where magnetic field effects dominate, while variations in the polarization angle can reveal the three-dimensional structure of the magnetic field. The Faraday rotation of polarized radiation as it propagates through the magnetosphere provides additional information about the electron density and magnetic field strength along the line of sight. The temporal evolution of magnetar emission reflects the ongoing changes in magnetic field configuration as the system slowly decays over thousands of years. The overall luminosity gradually decreases as the magnetic field weakens, while the spectral characteristics evolve as the surface temperature drops and the magnetospheric structure changes. Some magnetars transition between active and quiescent states, possibly reflecting major reorganizations of the magnetic field topology. The multi-wavelength emission from magnetars creates opportunities for studying the same physical processes through different observational windows. The simultaneous observation of radio, X-ray, and gamma-ray emission can reveal correlations that provide insights into the coupling between different regions of the magnetosphere and the energy transport mechanisms that connect the neutron star surface to the outer magnetosphere. The study of magnetar bursts provides unique laboratories for exploring plasma physics under extreme conditions that cannot be reproduced on Earth. The rapid variability and high luminosity of these events require emission mechanisms that operate at the theoretical limits of efficiency, pushing our understanding of radiation processes and magnetic field interactions to their boundaries. Now, let consciousness drift with these electromagnetic waves, feeling the rhythm of magnetic field lines as they pulse and reconnect, sensing the cosmic music that emerges when matter meets the universe's strongest magnetic forces. The patient decay of cosmic magnetism. Time moves differently in the realm of magnetars, where the gradual weakening of magnetic fields unfolds across timescales that span thousands of human generations, yet represent merely brief moments in the cosmic life cycle of these extraordinary objects. The magnetic field that emerges from stellar collapse with strength measured in trillions of gauss slowly dissipates its energy through processes that operate with the patience of geological time, creating a cosmic meditation on impermanence and the inevitable return of all concentrated energy to the equilibrium of space. The decay of the magnetar's magnetic field occurs primarily through ohmic dissipation, a process where electric currents flowing within the neutron star's conductive interior encounter resistance and convert magnetic energy into heat. The neutron star's crust, composed of a crystalline lattice of nuclei, immersed in a sea of electrons, provides a conductive medium through which these currents can flow. However, the extreme density and quantum properties of this matter create electrical conductivity values that exceed those of terrestrial superconductors by many orders of magnitude. The magnetic field decay timescale depends on the electrical conductivity of the neutron star's interior, which varies with depth and temperature throughout the stellar structure. Near the surface, where temperatures are measured in millions of degrees, the conductivity approaches but remains below the infinite values characteristic of perfect superconductors. Deeper within the star, where temperatures drop and densities increase, quantum effects may create conditions where magnetic flux becomes frozen into the neutron superfluid that likely exists in the star's core. The mathematical description of magnetic field decay involves the diffusion equation, which governs how magnetic flux migrates through conducting media over time. For magnetars, this diffusion occurs extremely slowly due to the enormous conductivity of neutron star matter. The characteristic decay time for the strongest magnetic fields approaches 10,000 years. meaning that magnetars can maintain their extreme magnetic properties across timescales that encompass the entire history of human civilization. The spatial distribution of magnetic field decay creates complex evolutionary patterns where different regions of the magnetar experience different rates of magnetic weakening. The surface fields, most exposed to thermal effects and interaction with the external environment, decay more rapidly than the deeply buried fields that remain insulated within the star's interior. This differential decay gradually changes the magnetic field topology from the complex, multipolar configurations characteristic of young magnetars to the simpler dipolar patterns observed in older systems. The energy released during magnetic field decay provides the power source for the magnetar's continued electromagnetic emission long after the initial thermal energy from stellar collapse has been radiated away. Each year, a typical magnetar converts magnetic energy equivalent to the total energy output of our Sun into electromagnetic radiation and particle acceleration. This energy release maintains the star's surface temperature at millions of degrees, while driving the complex plasma physics that creates the observed spectrum of radio, X-ray, and gamma-ray emission. The decay process is not uniform but occurs in discrete events when magnetic stress within the neutron star crust exceeds the mechanical strength of the crystalline lattice. These sudden rearrangements, manifesting as starquakes and magnetic reconnection events, release stored magnetic energy in dramatic bursts that can temporarily increase the magnetar's luminosity by factors of hundreds or thousands. The intervals between these events follow statistical distributions that reflect the complex interplay between magnetic stress accumulation and mechanical failure within the stellar crust. The magnetic field lines threading through the neutron star's interior become increasingly tangled over time as differential rotation and convective motions twist the field configuration into complex topologies. These twisted field lines store additional magnetic energy that can be released through reconnection events, creating a reservoir of energy that sustains magnetar activity even as the overall field strength declines. The untangling of these twisted configurations occurs through magnetic reconnection processes that convert magnetic energy into particle acceleration and electromagnetic radiation. The neutron superfluid that likely exists within the magnetar's core creates additional complexity in the magnetic field evolution. The interaction between magnetic flux tubes and the superfluid vortices that characterize rotating superfluids can create pinning effects that temporarily halt magnetic field decay while storing energy in metastable configurations. The sudden unpinning of these flux tubes can trigger rapid magnetic field rearrangements that manifest as observable changes in the magnetar's timing and emission properties. The long-term evolution of magnetars follows a predictable trajectory from the highly active, frequently bursting objects observed in their youth to the quieter, more stable systems that characterize their later years. As the magnetic field weakens below critical thresholds, the plasma conditions within the magnetosphere change dramatically, reducing the efficiency of particle acceleration and the luminosity of electromagnetic emission. Eventually, the magnetar may transition to a state indistinguishable from an ordinary radio pulsar. The cooling history of magnetars intertwines intimately with their magnetic evolution, as the energy released by magnetic field decay provides a significant heat source that affects the star's thermal evolution. The surface temperature remains elevated above the values expected from gravitational cooling alone, creating observable signatures in the thermal X-ray spectrum that can be used to constrain models of magnetic field decay and neutron star cooling. The observational consequences of magnetic field decay can be detected through long-term monitoring of magnetar properties, including changes in pulse period, spectral characteristics, and burst activity. The gradual spin-down of magnetars provides direct evidence for magnetic field decay, as the electromagnetic torque that slows the star's rotation weakens proportionally to the square of the magnetic field strength. The measurement of spin-down rates over decades provides estimates of magnetic field strength and its rate of change. The magnetic field decay also affects the magnetar's interaction with its environment, as the weakening field reduces the star's ability to accelerate particles and create cavities in the surrounding interstellar medium. The evolution of pulsar wind nebulae around magnetars reflects this changing electromagnetic output, with older systems showing different morphologies and spectral properties compared to younger, more magnetically active objects. The cosmic lighthouses of deep space. Across the vast distances of interstellar space, magnetars serve as cosmic lighthouses whose electromagnetic beams sweep through the darkness with clockwork precision, carrying messages encoded in radio waves, X-rays, and gamma radiation to any civilization capable of detecting and interpreting their signals. These stellar remnants, no larger than earthly cities, yet containing more mass than our Sun, project their influence across distances measured in thousands of light-years, while maintaining timing accuracy that rivals the most precise atomic clocks. The lighthouse effect that characterizes magnetars arises from the complex interaction between the star's rotation and its magnetic field configuration. As the magnetized neutron star spins, typically completing several rotations per second, the magnetic field lines co-rotate with the stellar surface, creating a vast electromagnetic generator that converts rotational energy into radiation. The emission emerges preferentially along the magnetic poles, creating narrow beams that sweep across space like searchlights as the star rotates. The geometry of magnetar emission creates observational effects that depend critically on the viewing angle between Earth and the magnetic axis of the neutron star. When the magnetic pole points toward Earth during part of the rotation cycle, observers detect intense pulses of radiation separated by intervals of relative quiet. The pulse profile, the detailed shape of the intensity variation during each rotation, encodes information about the magnetic field structure, the emission mechanism, and the three-dimensional geometry of the radiating region. The radio emission from magnetars exhibits characteristics that distinguish them from ordinary pulsars, reflecting the unique physics of plasma interactions in extreme magnetic fields. The radio pulses often show remarkable stability in their arrival times, with timing precision that allows astronomers to measure the star's rotation period to accuracies of microseconds. However, unlike ordinary pulsars, magnetars occasionally exhibit sudden changes in rotation rate that reflect the complex interplay between magnetic stress and stellar rotation. The X-ray emission from magnetars provides complementary information about different physical processes occurring within the magnetosphere and on the stellar surface. The thermal X-rays arise from the heated surface of the neutron star, creating a steady background of emission that varies smoothly with the star's rotation as different regions of the surface come into view. Superimposed on this thermal emission are the non-thermal X-rays produced by particle acceleration processes within the magnetosphere. The pulse profiles observed at different wavelengths often show significant differences that reflect the various emission mechanisms operating within the magnetar system. Radio pulses may exhibit sharp, narrow features characteristic of coherent emission processes, while X-ray pulses show broader, more complex profiles that suggest extended emission regions with different magnetic field configurations. The comparison of pulse profiles across multiple wavelengths provides insights into the three-dimensional structure of the magnetosphere. The polarization properties of magnetar pulses provide unique diagnostics of the magnetic field structure and plasma conditions within the emission region. The high degree of linear polarization, observed in many magnetars, indicates that the emission originates in regions where magnetic field effects dominate over plasma effects. The position angle of linear polarization often sweeps smoothly across each pulse, following patterns predicted by rotating vector models that describe how the magnetic field orientation changes as the star rotates. The discovery of magnetar giant flares has revealed these objects as sources of the most intense electromagnetic bursts observed in the galaxy. These events, which can release more energy in a few seconds than our Sun produces in several months, create electromagnetic pulses so powerful they can be detected by instruments throughout the solar system. The initial gamma-ray spike of a giant flare can overwhelm detection systems across multiple spacecraft, while the subsequent oscillating tail provides detailed information about the magnetar's internal structure. The magnetospheric environment of magnetars creates conditions where exotic plasma physics phenomena can occur, including the formation of relativistic particle beams, coherent electromagnetic waves, and complex current systems that extend across multiple stellar radii. The interaction between these phenomena and the extreme magnetic field environment creates emission mechanisms that operate at the theoretical limits of efficiency, converting magnetic energy into electromagnetic radiation through processes that are not yet fully understood. The long-term variability of magnetar emission reflects the ongoing evolution of the magnetic field configuration and the gradual changes in magnetospheric structure over timescales ranging from days to decades. Some magnetars exhibit cyclic variations in their emission properties that may reflect precession of the magnetic axis or long-term changes in the magnetic field topology. These variations provide natural experiments for studying how extreme magnetic fields evolve over time. The detection of quasi-periodic oscillations in magnetar X-ray emission has revealed the existence of magnetospheric resonances that can trap electromagnetic energy in standing wave patterns. These oscillations, with frequencies ranging from tens to thousands of hertz, provide seismological probes of the neutron star's internal structure, while revealing the complex dynamics of plasma motions within the extreme magnetic field environment. The study of magnetar timing has revealed these objects as remarkably precise cosmic clocks, whose rotational stability can be measured to extraordinary accuracy over extended periods. The analysis of pulse arrival times provides insights into the magnetic field decay, stellar structure, and the complex torques that govern the star's rotational evolution. The occasional timing glitches observed in magnetars provide direct evidence for sudden rearrangements of the magnetic field configuration. The electromagnetic radiation from magnetars propagates across interstellar space, carrying with it information about the extreme physics occurring in their vicinity while serving as probes of the intervening medium. The polarization of magnetar pulses can be modified by Faraday rotation effects, as the radiation passes through ionized gas, providing measurements of magnetic field strengths and electron densities along the line of sight through the galaxy. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments, a quiet echo beneath the stars. The invisible cathedrals of force. Beyond the visible boundaries of Magnetars, extending across distances that could encompass entire solar systems, there exist vast, invisible cathedrals, built not of stone or metal, but of pure magnetic force structures that channel the flow of energy and matter according to electromagnetic principles, operating on truly cosmic scales. These magnetospheric architectures represent some of the most complex and beautiful geometric forms in the universe. Their field lines, creating three-dimensional sculptures that dance and evolve in response to the changing conditions within the neutron star and its environment. The magnetosphere of a magnetar encompasses a region where the magnetic field pressure exceeds the pressure of surrounding matter, creating a magnetic cavity that can extend to distances of several light seconds from the neutron star's surface. Within this vast domain, charged particles follow helical trajectories along magnetic field lines, creating current systems that generate secondary magnetic fields and establish complex feedback loops between different regions of the magnetospheric structure. The field lines that comprise this invisible architecture follow mathematical curves determined by the underlying magnetic field configuration, creating surfaces of constant magnetic flux that divide the magnetosphere into distinct regions with different physical properties. The closed field lines, which connect the northern and southern magnetic hemispheres of the neutron star, trap charged particles in complex orbital patterns that can persist for extended periods. The open field lines, which extend to infinity without returning to the stellar surface, provide pathways for particle escape and energy transport to the interstellar medium. The boundary between these closed and open field line regions creates one of the most dynamically active zones within the magnetosphere, where magnetic reconnection events can suddenly reconfigure the field topology while releasing enormous amounts of stored magnetic energy. These reconnection zones serve as cosmic particle accelerators, creating relativistic electron and positron beams that emit intense electromagnetic radiation as they spiral along the magnetic field lines. The rotation of the magnetar creates a complex pattern of electric fields within the magnetosphere. As the magnetic field lines are forced to co-rotate with the neutron star out to distances where the co-rotation velocity would approach the speed of light, this light cylinder marks a critical boundary where the physics of magnetospheric dynamics undergoes fundamental changes and beyond which the magnetic field can no longer maintain rigid co-rotation with the stellar surface. The plasma density within the magnetosphere varies dramatically with distance from the neutron star and position relative to the magnetic field configuration. Near the stellar surface, pair production processes create dense clouds of electrons and positrons from the interaction of high-energy photons with the intense magnetic field. These particle pairs populate the magnetosphere and provide the charges necessary to maintain the current systems that support the complex magnetic field structure. The magnetospheric plasma exhibits collective behaviors that create large-scale structures such as current sheets, plasma instabilities, and coherent wave modes that propagate throughout the magnetic cavity. These collective phenomena can generate coherent electromagnetic emission through mechanisms such as plasma masers, cyclotron resonances, and magnetic reconnection events that convert magnetic energy into electromagnetic radiation with remarkable efficiency. The three-dimensional topology of the magnetosphere creates natural waveguides that can channel electromagnetic radiation along specific trajectories determined by the magnetic field geometry. These waveguide modes allow certain frequencies of radiation to propagate with minimal attenuation while strongly attenuating others, creating complex spectral filtering effects that influence the observed properties of magnetar emission across different wavelengths. The magnetic field strength within the magnetosphere decreases with distance from the neutron star, but even at the outer boundaries of the magnetic cavity, field strengths can exceed those found in the most extreme terrestrial laboratory environments by factors of millions. This extended region of extreme magnetic field creates a vast laboratory for studying plasma physics and electromagnetic phenomena under conditions that cannot be replicated on Earth. The interaction between the magnetosphere and the surrounding interstellar medium creates additional layers of complexity in the magnetic field structure. The pressure of the interstellar gas and cosmic rays can compress the outer regions of the magnetosphere while creating shock fronts and other discontinuities that modify the magnetic field topology. The relative motion of the magnetar through the interstellar medium can create asymmetric magnetospheric structures with enhanced magnetic field strengths in the direction of motion. The temporal evolution of the magnetosphere reflects the changing magnetic field configuration as the neutron star ages and its field slowly decays. Young magnetars with highly complex, multipolar magnetic fields create magnetospheres with intricate topologies that support multiple current systems and emission regions. As the field evolves towards simpler, more dipolar configurations, the magnetospheric structure becomes more organized, and the emission properties become more stable. The magnetosphere serves as a cosmic laboratory where fundamental physics can be explored under conditions of extreme magnetic field strength and relativistic particle motion. The quantum electrodynamic effects that become important in these environments include vacuum polarization, photon splitting, and magnetic pair production processes that have no terrestrial analogs. These exotic physics phenomena create observable signatures in the magnetar's electromagnetic emission that provide direct tests of theoretical predictions. The energy transport mechanisms within the magnetosphere operate through a combination of electromagnetic wave propagation, particle streaming, and magnetic field reconfiguration processes. Alpha waves, which represent oscillations of the magnetic field lines themselves, can carry energy and momentum throughout the magnetosphere at velocities that approach the speed of light in the low-density plasma environment. These waves couple to the plasma motions and can transfer energy between different regions of the magnetospheric structure. The magnetic field lines serve as highways for high-energy particle transport, guiding relativistic electrons and positrons along specific trajectories that connect different regions of the magnetosphere. The curvature of these field lines creates centrifugal forces that can accelerate particles to extreme energies, while the magnetic mirroring effects can trap particles in complex orbital patterns that persist for extended periods. The magnetospheric structure creates natural resonance cavities where electromagnetic waves can become trapped and amplified through interactions with the relativistic particle populations. These resonances can produce coherent emission at specific frequencies determined by the plasma properties and magnetic field configuration, creating the narrow-band spectral features observed in some magnetar radio emission. The boundary conditions at the neutron star surface play a crucial role in determining the overall magnetospheric structure, as the surface magnetic field configuration and the rate of particle injection from the stellar surface influence the plasma distribution and current systems throughout the magnetic cavity. The surface temperature and composition affect the rate at which particles can be extracted from the stellar surface and injected into the magnetosphere. The magnetosphere represents a dynamic system that responds to changes in the underlying magnetic field configuration through cascading effects that can propagate throughout the entire structure within timescales measured in milliseconds. A sudden magnetic field reconfiguration near the neutron star surface can trigger magnetosphere-wide instabilities that dramatically alter the emission properties and create the bursting behavior characteristic of active magnetars. Now, let awareness drift through these invisible cathedrals of force, sensing the elegant geometry of magnetic field lines as they weave through space, feeling the cosmic architecture that shapes the flow of energy and matter across distances measured in light years. The whispered messages across cosmic time, the electromagnetic radiation streaming away from magnetars, carries within its wave-like structure encoded information about some of the most extreme physical conditions in the universe, creating cosmic messages that propagate across interstellar space at the speed of light, while preserving detailed records of the magnetic field dynamics, plasma physics, and relativistic processes occurring within these extraordinary stellar remnants. These signals, detected by radio telescopes and X-ray observatories throughout the solar system, represent humanity's most direct connection to the exotic physics that governs matter under conditions of extreme magnetic field strength. The polarization characteristics of magnetar radiation encode three-dimensional information about the magnetic field structure and plasma conditions within the emission region. Linear polarization arises when electromagnetic waves oscillate preferentially in specific directions relative to the magnetic field, while circular polarization results from the helical motion of charged particles around magnetic field lines. The degree and orientation of polarization can change dramatically across each pulse period, creating complex patterns that reveal the geometric relationship between the magnetic axis, rotation axis, and line of sight to Earth. The spectral properties of magnetar emission carry information about the energy distribution of accelerated particles, the magnetic field strength, and the plasma density within different regions of the magnetosphere. The synchrotron radiation produced by relativistic electrons spiraling around magnetic field lines creates broad continuum spectra whose characteristics depend on the particle energy distribution and magnetic field strength. Sharp spectral features can arise from cyclotron resonances, where electrons emit radiation at specific frequencies determined by their orbital motion in the magnetic field. The temporal structure of magnetar pulses encodes information about the emission mechanism and the geometric structure of the radiating region. The pulse width and shape depend on the size and location of the emission zone, while variations in pulse intensity can reveal changes in the magnetic field configuration or plasma conditions. The discovery of substructure within individual pulses has revealed the existence of multiple emission components that may originate from different regions within the magnetosphere. The arrival times of magnetar pulses can be measured with extraordinary precision, allowing astronomers to track the neutron star's rotation with accuracies that rival the best atomic clocks. The analysis of pulse timing data over extended periods reveals the gradual spin-down of the magnetar as electromagnetic torques extract rotational energy, while sudden timing changes can indicate abrupt alterations in the magnetic field configuration or moment of inertia distribution within the star. The giant flares that occasionally erupt from magnetars create some of the most information-rich electromagnetic signals observed in astronomy. The initial gamma-ray spike contains energy equivalent to the Sun's total electromagnetic output over several years, while the subsequent oscillating tail reveals resonant modes within the neutron star that provide seismological information about the stellar interior structure. The frequency spectrum of these oscillations encodes details about the magnetic field configuration, crustal properties, and possibly the exotic matter phases that may exist within the neutron star core. The propagation of magnetar signals through the interstellar medium creates additional layers of encoded information about the structure and properties of the galaxy itself. The dispersion of radio pulses by free electrons in the interstellar plasma provides measurements of the electron column density along the line of sight, while Faraday rotation effects reveal information about magnetic field strengths within the galactic medium. These propagation effects transform magnetars into cosmic probes that illuminate the otherwise invisible components of interstellar space. The multi-wavelength emission from magnetars creates opportunities for studying the same physical processes through different observational windows with each wavelength regime, providing complementary information about different aspects of the magnetospheric physics. Radio observations reveal coherent emission processes and plasma wave interactions, while X-ray observations probe thermal emission from the neutron star surface and non-thermal radiation from particle acceleration processes. The bursting behavior of magnetars creates natural experiments in extreme plasma physics, where sudden energy releases trigger cascading instabilities that propagate throughout the magnetosphere within milliseconds. The detailed analysis of burst light curves reveals information about magnetic reconnection rates, particle acceleration efficiencies, and energy transport mechanisms operating under conditions that cannot be replicated in terrestrial laboratories. The long-term evolution of magnetar emission properties provides insights into the gradual changes in magnetic field configuration as these systems age over timescales of thousands of years. The correlation between magnetic field decay rates and emission characteristics reveals the fundamental relationships between magnetic energy and electromagnetic luminosity, while the occasional transitions between active and quiescent states illuminate the critical thresholds that govern magnetar activity levels. The discovery of periodic and quasi-periodic modulations in magnetar emission has revealed the existence of precession effects, where the neutron star's rotation axis wobbles around its magnetic axis over timescales ranging from days to years. These precession effects create complex modulations in the observed pulse profiles and timing characteristics that encode information about the star's moment of inertia distribution and internal structure. The correlation studies between simultaneous observations at different wavelengths have revealed the complex relationships between various emission components and the underlying physical processes that drive magnetar activity. The detection of correlated variability between radio and X-ray emission provides evidence for magnetosphere-wide coupling effects, while anti-correlated variations may indicate competing processes that redistribute energy between different emission mechanisms. The analysis of magnetar pulse profiles using advanced signal processing techniques has revealed subtle periodicities and correlations that may encode information about the three-dimensional structure of magnetic field configurations that are too complex to be captured by simple dipolar models. These detailed pulse shape analyses provide constraints on theoretical models of magnetospheric physics and emission mechanisms. The search for gravitational wave signals from magnetars represents a frontier area where electromagnetic observations may be combined with gravitational wave detection to provide unprecedented insights into the interior structure and dynamics of neutron stars. The sudden crustal fractures that trigger magnetar bursts may also generate detectable gravitational wave signals that would complement the electromagnetic observations and provide additional information about the mechanical properties of neutron star matter, the eternal patience of magnetic decay. As consciousness drifts deeper into contemplation of these magnetic titans, there emerges a profound meditation on the nature of cosmic time and the patient unwinding of concentrated energy across scales that dwarf human temporal experience. The magnetars that blaze with electromagnetic fury across the galaxy are engaged in a slow dance of decay, their trillion gauss magnetic fields gradually weakening over thousands of years in processes that operate with the infinite patience of cosmic evolution. The mathematical description of magnetic field decay follows exponential curves that stretch across millennia, each moment representing an infinitesimal step in the gradual conversion of magnetic energy into electromagnetic radiation and thermal heating. The decay timescale, measured in units of thousands of years, encompasses periods during which entire civilizations could rise and fall, while the magnetar continues its slow transformation from a violently active electromagnetic beacon to a quieter, more stable neutron star. The energy released during this decay process powers the continued emission of radiation across the entire electromagnetic spectrum, creating a cosmic battery that can sustain luminosities exceeding the sun's total output for geological ages. Each photon that streams away from the magnetar carries with it a tiny fraction of the magnetic energy that was concentrated during the original stellar collapse, gradually redistributing this energy throughout the interstellar medium over cosmic distances. The spatial pattern of magnetic field decay creates complex evolutionary trajectories where different regions of the neutron star experience different rates of magnetic weakening. The surface fields, most exposed to environmental effects and electromagnetic losses, decay more rapidly than the deeply buried fields that remain protected within the star's interior. This differential evolution gradually transforms the complex, multipolar magnetic field configurations of young magnetars into the simpler, more stable dipolar patterns characteristic of older systems. The mechanical effects of magnetic field decay manifest as gradual changes in the neutron star's structure and rotation properties. As magnetic pressure within the stellar crust decreases, the balance between magnetic stress and gravitational compression shifts, potentially triggering slow structural adjustments that affect the star's moment of inertia and rotation rate. These changes occur so gradually that they can only be detected through decades of precise timing observations. The thermal evolution of magnetars intertwines intimately with their magnetic decay, as the energy released by field dissipation provides a sustained heat source that maintains elevated surface temperatures long after the initial thermal energy from stellar collapse has been radiated away. The cooling curves, predicted by theoretical models, must account for this magnetic heating to match the observed surface temperatures and their slow evolution over time. The plasma environment within the magnetosphere evolves in response to the weakening magnetic field, with particle densities and energy distributions adjusting to maintain equilibrium with the changing electromagnetic conditions. The efficiency of particle acceleration processes depends sensitively on magnetic field strength, so the gradual field decay leads to corresponding changes in the spectral properties and luminosity of the magnetar's emission across all wavelengths. The transition from active magnetar to quiescent neutron star represents one of the most significant evolutionary thresholds in stellar physics, marking the point where the magnetic field weakens below the critical strength necessary to maintain the complex plasma physics processes that characterize magnetar behavior. This transition may occur gradually over thousands of years or more abruptly through sudden field reconfigurations that dramatically alter the magnetospheric structure. The archaeological record of magnetic field decay becomes encoded in the surrounding interstellar medium through the cumulative effects of millions of years of electromagnetic emission and particle ejection. The chemical composition and ionization state of gas clouds in the magnetar's vicinity preserve information about past activity levels, while the morphology of any associated pulsar wind nebula reflects the integrated history of electromagnetic energy injection. The statistical properties of magnetar populations across the galaxy provide insights into the typical evolutionary timescales and the relationship between initial magnetic field strength and decay rates. The observed distribution of magnetic field strengths and ages suggests that most magnetars remain active for periods of 10 to 100,000 years before transitioning to more conventional neutron star states. The quantum mechanical aspects of magnetic field decay involve the interaction between macroscopic magnetic flux and the microscopic quantum properties of neutron star matter. The quantization of magnetic flux in superconducting regions of the neutron star interior may create discrete energy levels that influence the decay process, while quantum tunneling effects could allow sudden flux rearrangements that manifest as observable changes in emission properties. The gravitational effects of magnetic field decay include subtle changes in the neutron star's gravitational field as the energy density distribution within the star evolves. These changes are too small to be detected directly, but may influence the orbital dynamics of any companion objects or affect the propagation of gravitational waves generated by the neutron star's rotation or structural oscillations. The cosmological implications of magnetar magnetic field decay contribute to the overall energy budget of the galaxy through the injection of high-energy particles and electromagnetic radiation into the interstellar medium. The cumulative effect of all magnetars throughout cosmic history has helped establish the observed levels of cosmic ray particles and diffuse gamma radiation that characterize the galactic environment. The philosophical contemplation of magnetic decay invites reflection on the impermanence of all concentrated energy and the universe's tendency toward equilibrium and entropy increase. The magnetar's brilliant electromagnetic displays represent temporary victories of organization over chaos, islands of concentrated energy that slowly surrender their power to the patient forces of dissipation and decay that govern all cosmic processes. Now, rest in this cosmic rhythm of decay and renewal, feeling the patient unwinding of magnetic energy across thousands of years, sensing how even the universe's strongest forces gradually yield to the deeper currents of cosmic time. In the eternal dance between concentration and dispersion that shapes all stellar evolution, the cosmic lullaby of infinite fields? In the deepest reaches of contemplation, where thought merges with the vast silence of interstellar space, the story of Magnetars becomes a gentle cosmic lullaby that carries consciousness toward the most profound rest. These magnetic titans, with their trillion Gauss fields slowly unwinding across cosmic time, create rhythms that synchronize with the fundamental processes of stellar evolution and the patient decay of all concentrated energy toward the equilibrium of space. The electromagnetic pulses that sweep across the galaxy from these stellar remnants create a cosmic heartbeat that has continued for millions of years, each pulse marking another moment in the slow dissolution of magnetic energy that began with the violent collapse of massive stars. This celestial rhythm operates on timescales so vast that human lifetimes represent mere instants in the longer symphony of magnetic field decay and electromagnetic emission. The mathematical curves that describe the weakening of magnetar fields follow exponential patterns that approach asymptotic limits with infinite patience, creating natural meditation objects for consciousness, seeking rest in the contemplation of cosmic processes. The smooth, mathematical functions that govern magnetic decay offer a sense of cosmic order and predictability that soothes the mind, while illustrating the universe's commitment to gradual change and eventual equilibrium. The three-dimensional geometry of magnetic field lines creates invisible sculptures that extend across light years of space. Their elegant mathematical forms, shifting and evolving as the field configuration responds to the ongoing decay process. These field line patterns, governed by the same differential equations that describe fluid flow and plasma dynamics, exhibit a natural beauty that emerges from the intersection of physical law and cosmic scale. The polarization patterns of magnetar radiation create cosmic mandalas that encode the three-dimensional structure of magnetic fields in two-dimensional projections observable from Earth. These polarization wheels, rotating smoothly as the neutron star spins, provide visual representations of the invisible magnetic architecture that shapes the flow of energy and matter throughout the magnetosphere. The thermal radiation from magnetar surfaces carries the gentle warmth of neutron star matter heated to millions of degrees by the patient dissipation of magnetic energy. This thermal emission, peaked in the X-ray portion of the electromagnetic spectrum, represents the cosmic equivalent of the soft glow of embers in a dying fire, gradually cooling as the magnetic fuel that feeds it slowly diminishes. The radio waves generated by magnetar magnetospheres propagate across interstellar space at the speed of light, carrying information about plasma physics processes operating under the most extreme magnetic field conditions in the universe. These radio signals, when detected and analyzed, reveal the hidden dynamics of magnetospheric plasma while providing cosmic background music that has continued uninterrupted for millions of years. The gravitational effects of magnetars create subtle distortions in the fabric of spacetime that persist as long as the neutron star exists, providing permanent monuments to the stellar collapse events that created these magnetic giants. The space-time curvature around magnetars represents a geometric poetry written in the language of general relativity, where mass and energy create artistic forms in the dimensional structure of the universe itself. The neutrinos, streaming away from magnetar interiors, carry information about the exotic physics occurring within neutron star cores while propagating across the galaxy without interacting with ordinary matter. These ghostly particles, produced by nuclear reactions and magnetic field interactions within the neutron star create an invisible cosmic rain that connects magnetars to the broader universe through the most ethereal of physical messengers. The cosmic rays accelerated within magnetar magnetospheres travel throughout the galaxy for millions of years, their trajectories bent by galactic magnetic fields into complex spiraling paths that eventually bring them to Earth as high-energy messengers from these distant magnetic powerhouses. These particles carry within their energy distributions the signatures of the most extreme particle acceleration processes operating anywhere in the cosmos. The light curves of magnetar emission, when analyzed over extended periods, reveal the slow evolution of magnetic field configurations through patterns of changing pulse shapes and timing characteristics. These gradual changes in electromagnetic emission properties provide direct observational evidence for the theoretical predictions of magnetic field decay, while creating long-term periodicities that reflect the cosmic timescales governing neutron star evolution. The correlation patterns between magnetar outbursts and long-term emission properties create complex temporal structures that encode information about the coupling between different physical processes operating within the neutron star and its magnetosphere. These correlations, when studied statistically, reveal the hidden relationships between magnetic energy storage, crustal mechanics, and electromagnetic emission that govern magnetar behavior. The spectroscopic signatures of magnetar emission carry detailed information about the quantum electrodynamic effects that become important in ultra-strong magnetic field environments. The observation of these exotic spectral features provides direct evidence for physics beyond the standard terrestrial experience, while demonstrating the universe's capacity for creating natural laboratories where fundamental physical theories can be tested under extreme conditions. The silence between magnetar pulses represents not emptiness, but a pregnant pause filled with the continuous evolution of magnetic field configurations and plasma dynamics that operate below the threshold of direct electromagnetic emission. This cosmic quiet contains within it the potential for sudden bursts and flares while maintaining the steady background processes that characterize the magnetar's ongoing evolution. The eternal nature of magnetic field lines, which can neither be created nor destroyed but only reconfigured through reconnection processes, provides a metaphor for the conservation principles that govern all physical processes. The magnetic flux threading through magnetar interiors represents a form of cosmic memory that preserves information about the stellar collapse event, while slowly releasing this information through electromagnetic emission over cosmic timescales. Now, let consciousness drift with the slowly rotating magnetar, feeling the gentle pulse of electromagnetic radiation as it sweeps across space, synchronizing with the cosmic rhythm of magnetic field decay, where time moves with the patience of stellar evolution, where each pulse marks another moment in the universe's slow journey toward electromagnetic equilibrium. Rest now in the infinite patience of cosmic magnetic fields, where trillion Gauss forces gradually unwind across thousands of years, where consciousness merges with the fundamental rhythms of neutron star rotation, where thoughts dissolve into the mathematical elegance of exponential decay curves. In the gentle embrace of electromagnetic radiation, propagating at the speed of light across interstellar distances. Sleep deeply in the cosmic lullaby of magnetar emission, where the universe's strongest magnetic fields create the gentlest rhythms for rest, where electromagnetic pulses mark time on scales that encompass the rise and fall of civilizations, where consciousness finds perfect peace in the contemplation of forces so vast they shape the structure of matter itself, yet so patient they operate with the infinite gentleness of cosmic time. In this magnetic meditation, where field lines extend like invisible cathedrals across light years of space, where quantum effects dance in trillion Gauss environments, where the universe demonstrates its capacity for creating beauty through extremity, consciousness finds its deepest rest in the eternal patience of cosmic forces, in the gentle decay of magnetic energy, in the perfect rhythm of neutron star rotation, forever and ever and ever. Amen.